All right, kiddos, welcome back. We're continuing to talk about periodic properties, and we're continuing to talk at the beginning of this video about ionization energies. So just a quick review. If we go across a period, let's say from lithium to neon, that's period number 2. Let me show it to you in the periodic table. Period number 2, when we go from lithium to neon, the ionization energy increases. The energy required to take an electron away from the neutral atom increases. We look at the third period from sodium to argon, the ionization energy increases, and so on down the periodic table. So the question is, why does the ionization energy increase when we go across a period? So from the second period from lithium to neon, the ionization energy increases. And of course we saw the same thing in the third period, the fourth period, the fifth period, and so on. Do you recall why? What else happens when we go across a period? Why would it be more difficult to remove an electron from neon than it would be from lithium? That's right, because the atomic radius decreases. So those electrons are being held closer to that positive nucleus, and so they're more difficult to remove. Now, the other trend was when we went down a group. Let's say now we go down the noble gas group from helium to neon to argon to krypton to xenon. Obviously, you can see the trend is a decrease in ionization energy. So when I go from helium down to radon, it becomes easier to take an electron away. So we would say when we go down, ionization energy decreases. Do you remember why? Yeah, when you go down a group, you gain energy levels. The electrons are farther away from the nucleus. There's more shielding. The inner electrons are pushing the outer electrons out. So the ionization energy decreases because the atomic radius increases when we go down that group. Okay, and this graph here in your notes shows that quite nicely. Alrighty, now what I want to talk about today are successive ionization energies. So we've been talking about first ionization energies, and you can see in period number 2 from lithium down to neon that the ionization energy generally increases. Once again, that's due to the decrease in the atomic radius. What do you think second ionization energy means, or third ionization energy, or so on? Think about that for a second. What is second ionization energy? If you said the energy required to remove an electron from a positive 1 ion, you would be correct. See, we've already taken one electron away. So it's no longer neutral, it's positive 1. We've taken a negative charge away. So to take a second electron away, we have to take it away from a positive 1 ion. What do you think third ionization energy is? Yeah, if you said energy required to remove an electron from a positive 2 ion, you would also be correct, because we've already taken away 2 electrons by the time we get to the third electron. And so that's what those terms mean. Second ionization energy, third ionization energy, and so on. The unit that we're using here in this chart is kilojoules per mole of electrons removed from 1 mole of that element or ion. So let's take a look at this a little bit more in detail. Let's take a look at the element beryllium on this chart. And why do you think the second ionization energy of beryllium is higher than the first ionization energy? So let's use a different color here. Here's beryllium, kiddos. Notice it has 2 valence electrons. The first ionization energy is 900 kilojoules per mole. Remember, we're taking that away from a neutral atom. The second ionization energy is 1760 kilojoules per mole. Why do you think it's higher? Absolutely, because the second electron that we're taking away from beryllium comes from a positive 1 ion. So we have a proton to electron ratio that's higher than it was originally. Okay, so let's see if we can answer this question. Why do you think the second ionization energy is higher than the first ionization energy for beryllium? It's because the second electron is removed from a positive 1 ion. All right, now let's look at the third ionization energy for beryllium. So the third is 14,850 kilojoules per mole. That is a huge increase from the second ionization energy. So I think there's more going on than just taking it away from a positive 1 ion like we did in the previous ionization. So we notice that there is a huge increase in ionization energy. Let's write the electron configuration for beryllium, and let's see if we can figure out why there's such a big increase when we try to take that third electron away. Beryllium, kiddos, has 4 electrons, so its configuration would be 1s2, 2s2. Or I suppose we could write a shorthand version and say helium 2s2, couldn't we? All right, now, won't these first 2 electrons for beryllium, these 2 right here, when I remove them, won't they be relatively easy compared to the third electron that I have to remove? Because once the first 2 are removed, those 2 right there, won't I be taking it from an energy level that's even closer to the nucleus? Yeah, I've lost an entire energy level. So the third electron from beryllium has to come from the first energy level. So why is there such a big difference from the second to third ionization energy for beryllium? And that's because the third electron must be removed from a lower energy level, lower than the first 2 that I had to take away. So when that happens, when you get closer to the nucleus, it becomes even more difficult to remove that next electron. Let's take a look at the element boron, and we're going to look for the big jump in the element boron. So let's use a different color again. We'll go with green here. Here's the element boron, kiddos. The first ionization energy is 800 kilojoules per mole. The second ionization energy is 2,430 kilojoules per mole. The third is a bit higher, 3,660 kilojoules per mole. And the fourth is huge. It's 25,020 kilojoules per mole. Why would the fourth ionization energy for boron be so high? Well, let's write the electron configuration for boron. Boron, kiddos, has 5 electrons. So its configuration would be 1s2, 2s2, 2p1. Or we could write the shorthand notation, helium, 2s2, 2p1. Do you notice that it has 3 valence electrons? 3 electrons in the second energy level. It would make sense that those first 3 electrons were relatively easy to take away. But once I got to the 4th electron for boron, I then have to remove it from the 1s sublevel. And so I would get a huge jump on the 4th electron that I have to take away from boron. All right, well, let's see if you can figure this out on your own for the next few. Where do you think this big jump in ionization energies would occur for the following elements. So take a look at the periodic table. See if you can figure out where we get a big jump in ionization energy for sodium, calcium, and aluminum. So try to fill in these blanks. After you attempt that, come back to the video and let's see how you did. Alright, welcome back. Let's take a look at sodium first. So, sodium is not on this chart, so we can't cheat and find sodium here. So we're going to have to go to our periodic tables, kiddos. And here is sodium right here in the periodic table. Its electron configuration is neon 3s1. Alright, so sodium, its electron configuration is neon 3s1. So it looks like I can take away one electron pretty easily. True story, because it's in the third energy level. So after the first electron, it's not so bad to take away. So the big jump will be the second ionization energy. See, the first one comes from the third energy level. The next electron I would have to take away would come from an energy level that's closer to the nucleus. So the big jump in sodium I would suspect to be the second ionization energy. What about calcium? Let's take a look at calcium here. So calcium ends with 4s2. Okay, 4s2. So its configuration would be argon 4s2. So don't you agree that the first two electrons for calcium would be pretty easy? So after the second electron, we would get a big jump. So the third ionization energy for calcium would be really, really high because we take the first two from the fourth energy level. The next electron, the third, would have to come from a lower energy level. All right, let's try it with aluminum. So aluminum, kiddos, is right here. Its configuration is neon 3s2 3p1. So let's write that down. Neon 3s2 3p1. Don't you agree that I can probably take 3 electrons away pretty easily? These 3 in the valence level. So after the third electron, the big jump would be the fourth ionization energy. Because after the first 3, then I have to take it away from a closer energy level. Closer to the nucleus. We have a huge proton to electron ratio at that point as well. But the big thing is we're taking it from a lower energy level. All right, how did you do on those? All right, we'll probably review those in an upcoming video. All right, the next thing we need to talk about is something called electronegativity. So, the electronegativity of an element indicates the relative ability of its atoms to attract electrons in a chemical bond. Now, I'm going to stop the video here and just defining what electronegativity is and let you think about that over the next couple of days to think about what electronegativity really is and what you think the trend in electronegativity is when we go across a period and down a group. Okay, so I'll stop there for the day. Talk to you later. Bye-bye.